Okay, this is the fourth video for IB Quantum Mechanics. Today we're looking at something called matter waves and the de Broglie hypothesis. And the basic idea from the last few videos is that light behaves like a particle. It carries particular amounts of energies, and the energy carried by a particle of light, called a photon, is Planck's constant h times the frequency of that photon. It also turns out that light can carry momentum in much the same way. And a young French physicist by the name of Louis de Broglie came up with the idea that, well, if light can be described as a particle, even though we're pretty sure it's actually a wave, maybe electrons, which we're pretty sure are particles, can be thought of as waves as well. And he said, well, to be consistent with the quantum mechanics, with what we know about light, the wavelength of an electron would be given by h over p, where h is Planck's constant and p is the momentum of the electron. The idea being that as the electron speeds up, its momentum increases, and that means its wavelength decreases. So we want to find the wavelength of an electron moving at 10 to the 5th meters per second. Well, Planck's constant, 6.626 times 10 to the negative 34 joule seconds, divided by the momentum of this electron, and momentum is just mv, so mass of an electron, 9.1 times 10 to the negative 31 kilograms, times a wavelength of 10 to the 5th times a velocity of 10 to the 5th meters per second, and we get out the calculator, and what do we get? We find that the wavelength of this particular electron is 7.28 nanometers. In general, if you have something with a long wavelength, it acts more like a wave, and something with a short wavelength acts more like a particle, classically. But with quantum mechanics, which is what all of modern physics is based on, everything is both a particle and a wave. And it turns out the wave descriptions of it are usually more useful than the particle descriptions. So de Broglie has this hypothesis. It turns out to be true, which is why you're learning it today. But what experiments were done? Oh, we won't do that example. What experiments were done that convinced physicists that he was actually right? And it turns out that the way you show light as a wave is Young's double slit experiment. You get an interference pattern. If you want to show that an electron is a wave, you have to find a way of producing an interference pattern with electrons. And so we need to shine electrons on two sources like that. But because the wavelength of electrons is on the order of nanometers, we need really, really small distances. Remember, light has a wavelength on the order of hundreds of nanometers, and we can observe a Young's double slit with d on the order of 1/10 of a millimeter. Because electrons have a much shorter wavelength, we need a much smaller d, and we can't just make it by putting two slits in a photographic plate. Simply can't get them too close enough together. So what they did is they used a crystal. I believe it was a salt crystal. And the idea is that you have a beam of electrons coming in like this, and some of those electrons bounce off of the first crystal plane, and some of those electrons bounce off the second crystal plane. The result is that the second beam of electrons has a slightly longer path length. And that means that because there's a path length difference, there's the potential for interference between the two different paths. And that is exactly what they found. As they changed the angle, they found that the intensity, the number of electrons that were detected at the detector, changed. And there were a couple of particular angles that gave them constructive interference, and a couple that gave them destructive interference. Classically, what you'd expect to see is that. A more or less featureless curve, slightly decreasing, but nothing terribly interesting. What they actually saw was an interference pattern, and that tells us that electrons are in fact waves. Similar experiments have been done with neutrons as well. Protons are somewhat more difficult, but we've done experiments like that with protons as well and a variety of other particles. And it turns out that all particles are waves, all waves are particles. There's not really much of a difference. What you need to know is the de Broglie hypothesis. You need to be able to state the associated equation, lambda equals h over p. And you should be able to describe the setup used in the Davison-Germer experiment, which is the shining electrons on a crystal and looking for interference patterns.